Alright, in this second axial deformation example, note we've got this long rod that has two different concentrated forces on it, and that's kind of different and interesting. Now notice the units of the force in K, that means kips, so 70,000 pounds in one location, 30,000 pounds in another location, and the member has segments here, 8 feet, 6 feet, and 4 feet. This part that's just hanging out here at the end, they're 18 feet long, 1.5 inch diameter. Oh wow, so this is not drawn to scale here. This is a long, skinny kind of rod. It is a steel tool alloy, L2. Yield stress is pretty high. That's 85 KSI. That's pretty high for steel. Modulus of elasticity is typical steel, 29,000 KSI. And we're going to ignore buckling. We want to find the displacement of point A, where, oh, we don't have an answer. Well, here's the thing. I'm going to take a big gigantic guess here that let's look at an approximate stress. I'm not even going to do anything very sophisticated. I'm going to say, all right, sigma approximately is, oh heck, 70 and 30 and I don't know, they're going in different directions, but hey, this will be really wrong. But 70 kips divided by a cross-sectional area that I know is pi r squared, but let's just pretend it was a square at 1.5 inches, which would be too much area. So what if we shrunk that down and said it was about a square that was 1 inch by 1 inch, which would give us a 1 square inch area, which would give us a 70 KSI applied stress, which is still less than the proportional limit. So hey, this is elastic. So I'm guessing that we have elastic behavior. And then I'm going to say, okay, well, look at this. We've got 18 feet long. I know this is going to be totally wrong, but delta equal to NL over AE, that's our stress, sigma equal L over E, and everything's a big, huge approximation here. And so we're going to use our approximate stress, which is way wrong, but 70 KSI times our length, 18 feet. Let's put it into inches because I'm going to guess we're on orders of inches. Because look at this huge number that we're dividing by, 29,000 KSI. And so just as a crude approximation, 70 times 18 times 12 divided by 29E3, and that's about 0.5 inches. Right, so we're on a scale of inches. That's my guess of it. I was going to start off this by saying about 1 inch. I have not executed this problem in a long time. So you're getting to see this live of my pure raw guessing and how I might go about it. All right, so now let's see what really happens. And note that we've got different concentrated forces. We do not have a axial force that's going to be constant through the entire length. We'll have segments, but not all of it. Right, so we're going to create what's called the axial force diagram. We're going to create free body diagrams that are in between where all the loads are applied. So I've got 3 little squiggles I just did. We'll do a little free body diagram right here. There's point A, and we'll come along, and that's less than 4 feet, maybe 2 feet out there in the middle, and we're going to show the axial force in tension as positive. So tension equals positive. And that's the segment from A to B. And note, there's nothing else to show on that free body diagram because the 30 kips is applied over at B. It's not, we're really just chopping that little piece of the wacky fun noodle out there. And so therefore this is simple and trivial. NAB is going to be equal to 0. It doesn't have any axial stress. Doesn't mean it doesn't have displacement, but it doesn't have axial stress. Right, because the rest of this thing that it's connected to is going to move around. Right, so now we'll extend this, and there's point A, there's point B, and so now we have our axial force in BC, but in the free body diagram we've got our 30 kips that's applied at B. And we have a pretty trivial equation of equilibrium here. We can see that NBC is going to be in tension, and it's going to be equal to a plus 30 kips, meaning that's the tension part. And then finally we'll do the same thing, free body diagram that goes all the way past C from A. You wouldn't have to do it there, I'm going to choose to. And you say, well, couldn't I gone all the way to the support? Won't it be the same? And that's why I say you don't have to do it in between C and D. It's going to be the same because there's no other applied forces, right? So we got two of them though here. We got the 30 going to the right. We got our 70 going to the left. And that's going to mean there's a net of 40 to the left. NCD is going to have to go in the opposite direction. And it'll be in that fairly trivial axial equilibrium equation. It's got to be a minus 40. The minus 40 means that we actually end up with compression in that segment. So we have portions of this rod that have no elongation or shortening. That's out here in AB, but it does displace. BC is going to elongate a little bit, and CD is going to shorten a little bit. That wasn't my model at all over here. I just took 70 and I said, oh, I'm going to elongate it or shorten it. I don't know what. I didn't even look at what I was doing. Right? I'm just making a lot of crude assumptions up here about the ½ inch, and now it's far more complex than that. So here's our axial force plot. We just take what we just discovered. To the far left at D will be 0. Out here is A, and then we got B 4 feet to the left of A, and C is 6 feet. Oops, I didn't do that right, because 8 feet happens between C and D. Right? And now you come along and say, all right, let's just plot this. We've got 0 axial force right there. Between B and C we have 30 kips of tensile force, and we have 40 kips of, and that's minus 40 at both ends. And what I do is I just go ahead and put these little vertical bars. That's the discontinuity. Notice they're exactly equal to the concentrated force, right? We got 70 kips here at C, we got 30 kips here at B, and the reaction was 40 kips, and that's why you have that discontinuity. In other words, this axial force plot is just like a shear force diagram for beams. Very similar in how we might construct that. Okay, so now we come back and we say, all right, our basic model is still, right, delta equal our NL over AE. However, note we do have a centrically loaded member. It is prismatic, same cross-sectional area and same member properties, but because the axial force changes, we can't directly use NL over AE. Instead, we'll have to sum up the effects in each segment. Now, if the A and the E were changing along the way, we could include that right there, but hey, you know, the only thing that changes is the N and the L in each one, so we can actually pull out as a constant the A and the E. Right, so let's go find out what AE equals. That will be pi times R. That's not 1½ inch, it's 0.75 inches squared, and then we got 29,000 kips per square inch. We're going to get something that's in units of force when we're done with that. 0.75 inverse squared times 2983 is 1/6. That's kind of a big number. It's going to get bigger when we put in the pi. I'm going to leave it right like this. This is going to be 16,312.5 pi kips. Okay, I'm going to leave that in there. And so now, when that's factored out, I've got 1 over 16,312.5 pi kips times, and then we sum up all the segments that we've got here. We'll go left to right. We'll take this one, minus 40 kips times that length, 8 feet. We already have kind of figured out that this total is going to be a small number, so we're going to convert right away into length in terms of inches. That minus sign is really crucial. That means compression, shortening, right? And then the middle segment we got BC, that's 6 feet, and at 30 kips of elongation, so 30 kips, 6 feet is 72 inches. I'm just going to put that in directly. And then the last one has 0 axial force, and it's 48 inches long. course, I really don't need to put that in there mathematically, but there for completeness it is. Now I'm going to guess that we're going to have a number that is smaller, probably a lot smaller than a ½ inch. The reason why is because this assumed that we had 70 kips of axial force throughout the entire thing. We don't. We clearly do not. And didn't regard what would happen with the shortening and the compression, so that changes things too. We've got a little bit of shortening, we've got a little bit of elongation. You know, who's is duking that out? What's going to happen with the end displacement? I don't know which one of these wins out. Looks to me like probably I think we're going to have shortening, because look what happens here. 40 is bigger than 30. It's a negative. We've got the longer length there. Everything says that this is going to end up shortening, that end A is actually going to end up moving to the left. Let's find out what happens. Right? So I've got the 16,312.5 pi, well, just the 312.5 is in memory, and so now we've got 40, negative, times 8 times 12 plus 30 times 72. That's a net of minus 1680 kip inches. That's going to get divided by our 16,312.5 and divided by pi, and we get a small number that's minus 0.0328 inches. Wow. So that minus sign is telling us that, hey, positive was tension. That would have meant A moved to the left, and so we have delta at A, that's really what we were calculating, is equal to a 0.0328 inches to the left, which, hey, that could be kind of confusing. What do you mean by that? It would be better just to say we have shortening at the end of the member. Or you could just indicate that positive means elongation, and therefore the answer really would be the minus 0.0328 inches. Got to be careful in how you decide that you want to articulate all these answers. There's more than one correct way to do that.